On this video, I want to talk about the car on a banked curve. And so this is the type of problem that we have that occurs in your problem sets and might occur on the exam. So there's a car racing around, and we can imagine the track is banked. And let's just say the whole thing is traveling in some sort of circular banked track like this. The car is going around and around. And as it goes around, it's not really flying off the curve at all. It's being held there somehow. And we can imagine that there's no friction here. And you might ask, well, how is the car held on the curve? Why doesn't it just slide off as it travels around and around? Well, the reason for that is that there is some force that must be pushing it in toward the center. And this is the center-seeking or centripetal force. And one of the things that could be asked, for example, is what angle do we have to bank the curve at in order to provide a centripetal force that will keep the car from sliding off? So I'm going to do an analysis of this based on Newton's laws. And in it, we will draw on aspects of circular motion, which was in chapter 5. So let's take a look at this. I'm going to draw a force diagram for the car. And to make that a little bit more visible, what I'm going to do is copy this guy and put it down below. Copy. Okay, let's put it down here. And then I'll be able to draw a force diagram. Okay, so let's go for it here. So the forces acting on the car, you should know, are mg. So this is the weight of the car pulling down. But then there's also going to be a force that's perpendicular to the plane. And this is the normal force. It's acting out like that. And I'm just going to move this slightly to the side over there. These are the only two forces acting on the car. Now, if it's traveling in a circular track, then what that means is that it is being accelerated in toward the center. So there's some sort of force that's moving it in the direction of the arrow that I just drew here. How could that happen? That can't really come from mg because it's pointed straight down. So it has no component that's acting in the horizontal direction like this. It's got no component that's doing that. So what I want to know is how could I possibly get a horizontal component that's moving the car toward the center? In order to figure that out, what we have to do is take a look at the normal force. If I take the normal force and I decompose it, I could potentially get a component of it that's acting in this direction toward the center. So the set of axes that I want to establish for this description of what's happening are like this. I'll say that this is the direction toward the center of the track. I'll call that the r-axis, and I can call this the y-axis, like that. You could also think of the radial axis as being like the x-axis. So this is my set of coordinates, the y-axis here, and the x-axis or the radial axis like that. So what I want to do is I want to resolve the normal force such that its components lie along these axes, the y-axis and this horizontal axis. So the way I can do that is I can draw dashed lines like this and dashed line like that. These are 90 degrees. And so my hypotenuse here is, let's just draw it again in this color. My hypotenuse is this, that's the normal force. And now what I have is I have these components. I've got a component here, a vertical component along in the y-axis direction. And then I have another component that is, let's just go back to black, is here along the horizontal direction like that in the x direction. I want to resolve these guys, and it turns out that this angle here is theta right there. Okay, that angle is similar to this angle here, similar triangles again. And so I can say that this is going to be the normal force times the sine of theta, because it's on the opposite of the angle. And then this is going to be the normal force times the cosine of theta, because that is the adjacent side to this angle theta right here. Now with that, I can now move to write some equations. I can say the sum of the forces in the y direction equals the mass of the car times the acceleration it experiences in the y. I can also do an equation like this in the radial direction. The sum of the forces in the radial direction equals the mass of the car times the acceleration in the radial direction. So we'll get to these separately. Let's do the y first. So in terms of y, what I have is mg pointing down, and I have the normal force times cosine theta pushing up. So I can say something like this. Normal force times cosine theta, times cosine theta cosine theta minus mg equals the mass of the car times its acceleration in the y direction. Now, when this car is going around and around a curve, it doesn't really change its height. It doesn't really go up this way and it doesn't go down this way. For the most part, it's going to remain on the same section of the curve as it goes around and around and around like this. It's going to maintain the same height. So really what's going on is it doesn't accelerate at all in the y direction. This allows us to write this equation as the normal force times cosine theta equals just mg. Because this whole side equals 0, I can just add mg to both sides, and I get this equation. So that's my equation in the y. So far, so good. Now I'm going to get an equation in the radial direction, and once we get these two equations, we can eliminate some variables and come up with some sort of equation that's going to give me the angle here that I want. So let's do it for the radial direction. So in the radial direction, what do I have? I have a force that's pointing in this direction toward the center of the circle. Notice that it's not going down the plane. That's what we do when we're looking at the block on the inclined plane when it has friction or no friction. But for a car that's accelerating toward the center of a giant circle, it has to be horizontal. That's why we set up the axes in this way. Okay? So what I want for that is the normal force times the sine of theta. That's the component that's pointing toward the center. So I say normal force times sine of theta. That's my force. That's the only force I have acting on it in the radial direction. And it accounts for the mass of the car being accelerated toward the center. Now, if it's being accelerated toward the center, I can call that centripetal acceleration. And, just to be very explicit about it, I can write the centripetal acceleration as mv squared over r. That's what centripetal acceleration means. Okay, so now here's my second equation for the radial direction of the car on the inclined plane. Again, notice that in this case, I am not resolving mg, which we did for the inclined plane. Here, I'm only resolving the normal force, because the normal force is what provides a component acting in the direction of the circle pointed toward its central point. So this is like a radius of the circle pointing in that way. Okay? So it's a different concern. With the block down the plane, we were concerned with it sliding down. Now we're concerned with some force that's pointing horizontally toward the center. So I've got these two equations, and I want to somehow move them together in some way to get something that will give me the angle. So let's look at this equation. If I divide both sides by cosine theta, then I get this, mg over cosine theta. That equals the normal force. So now I can take this and I can insert it here in the other equation. That will allow me to eliminate this variable of the normal force. So let's write that. I'll say mg over cosine theta times sine theta. So I just inserted that equals mv squared over r. So that's a good equation that I can make some progress with. Let's move it over to the center here and work on it a little bit. Well, I can eliminate mass from both sides. So then I get g sine theta over cosine theta, and that equals v squared over r. And as I explained in a previous video, sine theta over cosine theta is just tangent theta. So I've got this, g tangent theta equals v squared over r. Now this equation can allow me to solve for the angle theta. If I divide both sides by g, I get this, tangent theta equals v squared over g times r. And if I want to know the angle, then I'm going to basically do the arctangent of this. I would then say arctangent, so that's the inverse tangent key on your calculator, v squared over g times r. That is going to equal my angle. Now, you could use this equation to solve for something else. Let's just say we gave you the angle and we gave you the velocity, but what we wanted you to determine was the radius of the curve. So you just take whatever variable you're interested in, you move it over to the left-hand side, for example, and then you express it in terms of all the other variables. So this equation here in the box can basically get you all those different things. So that's my hopefully clear and relatively quick explanation of the forces acting on a car on a banked curve.